So we're online. Good morning. Welcome on this dreary, cool spring morning. So yesterday we did anti-derivatives, and we basically reversed the derivative process. Welcome, Matt. So let's open it up with questions on anything from yesterday. Lesson 5.1, anti-derivatives.
I was wondering if we could go through 29.
Okay, 29. Let's locate that. So find an indefinite integral. Okay. Yeah, what do we do with 4 to the x, huh? Okay, I see where your question lies. Let's see what we got here. Let me write this down. Integral 2x minus 4 to the x dx. And this is number 29. Okay, now let's go back to our notes. So number 29. So, the question, I guess the big, maybe what we ought to do is, let me go back here and let's, I'm trying to think. Yeah, there's a page of derivatives in our lesson. Just need to find it. I must have missed it. It's somewhere where they had all the derivatives summarized. I don't have my physical, here it is. It's this one on the bottom here. So, David, the one you really need to spot is, I can't write on the screen, but it's this one, right? Yeah, it's this one where my cursor is, the second last one on the bottom right there. The integral of a to the x. You see that?
Yep.
That's probably what you need the reminder on. So when you take the integral of some constant to the x power with respect to x, that's equal to 1 over the natural log of that constant times, what it was originally. So it's itself divided by the natural log of its base. And then, of course, we got the plus c. So now, as we go to your problem, I mean, we all know what to do with the 2x, right? Up the power by 1. And then divide by that power. So it's going to be wind up being x squared. And now on that second part, here's where we're going to do that, what we did before. And that's 1 over the natural log of 4 times 4 to the x plus c. So the only thing we would do is simplify this part by just saying x squared. And this other part you could write like this. I mean, you could bring these two together up here so it reads. So that would, I mean, there's a couple different forms, but one of those should be what you wanted. So there's a case where you might have to look back to the reference page on remembering how do we take, what happens when you're dealing with a constant to the x power. Not the power rule, but it's that law. Other questions from last time? Okay, this was real interesting planning this. You know, here we're taking kind of half of a chapter, and yet I want to prepare you guys as well as possible for Calc 2. I know not all of you going on, but of course that's one of the top objectives of Calc 1 is to get everybody ready for the next stage. So anyway, as I was planning this, I mean, if I was doing it in the order of the book, and if we really had enough time to do the entire chapter 5, then I would go at it a little bit more slowly, and I wouldn't, so to speak, spill the beans as quickly. But I have to show you guys the complete picture, otherwise you won't really get the purpose of what we're doing. I don't know if that makes any sense, but I'll try to explain it as we get going. So here's the second lesson. It's called area. And I already clued you in on the fact that the whole idea of an integral is that eventually it allows you to find the area under any shape whatsoever between two endpoints. And hence, we need to talk about area. Maybe not to the extent that the book does, but nevertheless enough that you can see what's going on. You can see there are some subheadings under there. Use sigma notation. So we're going to be using, we'll be bringing the Greek letter sigma into the effect here. When you take Calc 2, there's a lot of sigma notation. We are going to get just enough of it here so we can see what's going on. Understand the concept of area, approximate the area of a plane region. So I mean, some of this even goes into the struggles, for example, when they first how did they find the area formula for a circle? Well, what they did is they tried playing around with putting a regular polygon that had so many sides that it was almost round. And then they used the formula for finding the area of the regular polygon with n sides. And eventually, if you could take the limit of that, you arrive at this perfectly round thing. Well, that's kind of the concept that they talk about in chapter 5. So what one way of looking at it is, it's a bunch of rectangles added up. Here, I'm going to zip ahead and show you a picture. So from later in this lesson, here's a picture of a curve. It looks like a half a parabola, and underneath it, you can see we have 5 rectangles. Aren't perfect, but they kind of, if you add up the area of those rectangles, you would be a little bit short, right? You'd be a little bit under the area of the curve underneath the parabola. And if you did the rectangles that are on the top, like this, and added up those areas, you would be a little bit over. And then by using limits, you can kind of figure out, oh yeah, well it's in between, and we can actually find the area. Well, that's the idea. Because you're adding up rectangles, you will see that we need to use this adding up notation called sigma notation. The Greek letter sigma, that's the Greek capital S, and the Greek capital S stands for sum. So let me read you this notation. So it says the sum of n terms, A1, A2, A3, all the way up to A whatever, n. This is how it's written. And in particular, what you want to make note is this part. I mean, that's the notation. So you see under and above the sigma notation, there's an I equals 1, and on top there's an N. That's just telling you start when I is 1 and keep going by ones until you reach N. That's all that means. And add them all up. Add up A1 plus A2 plus A3 plus A4 all the way till you get to whatever the nth one is. They call I the index. You don't have to remember this, but I just keeps track of which one you're on. And A sub I means the ith term. The A sub 1 means the first term, A sub 3 means the third term, and A sub I just is generic whichever term you're on. Okay, and if you get to A sub N, you've reached whatever the last term is. Add them all up. And now maybe you see why, because we're trying to add up areas. So here are some examples of sigma notation from the book. And I mean, the first one says, all right, just add up the numbers from 1 to 6. That's what that notation. I'm going to make this a little bit bigger so you can see it a little bit better. Hopefully that helps a little bit. And then maybe I'll even do this. Okay. And I should get rid of the pictures. There we go. Eventually I'll catch up here. So that first one, A, says add up all the numbers from 1 to 6. That's what that notation means. The second one says start at 0 and go to 5 and add up all the I plus 1s. So if I is 0, I plus 1 is 1. And then you go to the next one. I equals 1. I plus 1 is 2. So one thing you should notice, and I get my pen going here again, is that these two actually have the same result. It's add up the numbers 1 through 6. So interesting little tidbit here. Not unlike math, there's more than one way to do the same thing. Okay, let's look at the third one. The third one says, this time we're going to call our counter J, start at 3 and end at 7, and add up whatever J squared is. So for example, the first time when J is 3, 3 squared is, of course, 9, and then next 4 squared. So, and of course we could go ahead and do the arithmetic. Okay, now I want to go down to the bottom one, because eventually we want to add up areas. You're going to want to add up what? A rectangle. If we think back to this picture here, this picture we were looking at earlier, if we want to add up those rectangles, then we have to, the areas of them, then we have to do length times width in each case. Okay, and back where I was, I mean, this is basically the width of those rectangles, delta x, how far you're moving over each time, and this is the height. The y coordinate of the function, f of x, whatever number you're on. So basically what you're doing is taking the area of rectangle 1, the area of rectangle 2, all the way down until you get the last one. So this one down here is kind of what is the most important one on the list, and it's like saying, all right, what if we add up many rectangles? And by the way, I've got a little animation I want to show you. I'm spilling the beans here, but if you look at this page, now that I've made it bigger, you can't see it as well, but if you increase the number of rectangles, what happens? Well, the area of the rectangles is going to get closer and closer to the area of the curve, isn't it? And so guess what's going to happen eventually? We're going to take the sum of all these rectangles, and then we're going to take the limit as n approaches infinity. And I mean, technically, you could think of infinite number of little rectangles there. And when you do that, wow, we're right on. Like right now, we got big errors. The rectangles overlap. But as you get more and more of them, it gets closer and closer to the real curve. And that's this good old limit process, which we have used quite a bit in calculus. So, wow, I didn't expect to go out of order like that, but that's okay. So that's kind of what we're doing here. We're saying, oh, let's divide that up into little rectangles. And then if we take more and more of the rectangles and maybe even take a limit, guess what? We're going to get the area under the curve. Okay, a little historical note here. I don't think I've told you this before, but it's an interesting little anecdote from the past. So it goes like this. Carl Gauss, famous mathematician, was in elementary, or was in school. And I don't know, the teacher probably had a headache, and he was sick and tired of the noise, and he said, all right, I want all of you to sit down and add up the numbers from 1 to 100. And maybe he could have a few moments of peace. But very soon after that, Gauss is raising his hand, and he finds the answer very quickly. Here's what he did. Clever idea. He says, well, if I write the numbers 1 plus 2 plus 3 all the way up to 100, and underneath it, if I do it backwards, 100 plus 99 plus 98 all the way down to 1, when I add up those columns, they all come out to 101. The only problem is we're going to have twice because we've done 2 of them. So here's what he said. So what we've got is 101 100 times divided by 2. And he had the answer. And that is the correct answer, 5,050. So now what Gauss did is, well, he came up with one of the theorems. And the theorem is this one on the bottom of the page. Excuse me. Sorry about that. So if you add up the first n numbers, it's the same as taking n times n plus 1 divided by 2. That's what Gauss basically figured out. Now, you don't have to remember that theorem, but there's going to be like 4 or 5 of those that to show you can prove to be very helpful. Now, if we were really going into a detailed chapter 5 study, I might have you learn this, but right now, just see that there are some really cool rules that are basically shortcuts. Here are the 4 that they give you, and this is the one right here that I just showed you. Okay, that's the one that Gauss made use of. And he did it just by this really unique idea, writing out the numbers from 1 to 100 and then doing it backwards and then adding them up. It's, by the way, kind of interesting. A lot of theorems are discovered by people using their imagination in a way like that and discovering, holy cow, I just discovered a shortcut. So anyway, the first one is pretty obvious. If you add up the same number n times, isn't that the same as multiplication? So if I add up 5 9 times, isn't that just 9 times 5? So that this number 1 here is not worth much. I mean, that's just having trouble getting the pen going here. Yeah, whatever. I'll get my. So this one here isn't really very special. We could have figured that. Anybody could have figured that one out. This is the one we just got from Gauss. And then number 3 says, hey, if you add up a bunch of squares, which we did have for one of our problems a few minutes ago. Do you remember that? I don't remember where we were. Yeah, right here. So you see how in part C we had to add up a bunch of squares? So here's a shortcut that could have been used had we known about it. You can take the number n times n plus 1 times 2n plus 1 divided by 6. You know, you're sure not going to think of that one real easily in your head. And number 4 says, here's a shortcut for adding up cubes. So again, don't learn these, but you may want to make use of them. If we were doing a detailed study at this time of these sums, then I would have you learn this. Okay, so let's just take a look at example 2 where we evaluate a sum. You see at the top there we have evaluate the sum of I plus 1 over n squared for I equals 1 to n. All right. Now, you're going to notice we can use some techniques to simplify the sum. So, in this row, you see how they pulled the 1 over n squared out? Now, n is a constant. N is given, and you can see later they're going to ask you for these different values of it. So, like if we did it for n equals 10, so this is just 1 over 100. I mean, this n squared on the bottom. So we can pull the constant out. So just like we learned with integrals and with derivatives, you can pull the constant out. So we pull it out, and what's left is two things. Well, it's I plus 1, which you can change into two separate sums, the sum of I and the sum of 1. Well, the sum of I, hey, we just learned a shortcut for that just a few seconds ago. Remember that? I'll just show you real quickly. It's that number 2 one right there. The sum of whatever the index is up to is n times n plus 1 over 2. So you'll notice in this problem, we just substituted that, n times n plus 1 over 2. And then what happens when you take the sum of 1 n times? Well, that's just n times 1, n. Anyway, then by doing a little bit of algebra, you can actually simplify this thing down to this expression, n plus 3 over 2n. Well, now it's simple. What's the answer if n is 10? Just plug in. You get 13 on the top, and you get 20 on the bottom, and 13 divided by 20 is that 0.6500 down there. Anyway, and then do it for n equals 100 and 1,000, and then they ask you to do it for 10,000. Do you notice how the answer seems to be approaching something? It seems to be approaching 1/2. Do you see that? It's like a limit. And sure enough, if you look on the bottom, well, what's the limit of n plus 3 over 2n? All I did was all we did was take this expression, and now let's take a look at its limit as n approaches infinity. And you can split it up and look right here. To make this story a little bit shorter, what's the limit of 1/2 plus 3 over 2n as n approaches infinity? Well, the limit of 1/2 doesn't change. That's 1/2. And what happens when n approaches infinity in the second fraction? 3 over 2 times infinity? That's going to be 0. Oh, yeah. The limit really is 1/2. And again, we touch this concept of the limit in calculus. So, I mean, anyway, that's what they're trying to show you in this example too. So they were trying to show, hey, by looking at a chart and just taking n and increasing it like we did right here, we noticed that this seemed to be approaching 1/2. And then with a little basic limit notation, we found out, yeah, there really is a limit. That's where it's headed. Okay, then this is a repeat slide. I've already shown you this. If you add up all the rectangles, I just wanted to show you that if you get if the lower ones, the rectangles that are under the curve, like in part A up here, there they got this answer. And if you do it with the rectangles that are over the top, then we got this answer. And obviously the answer is somewhere in between, right? Because, you know, we're under, we're over, somewhere in between should be the answer. And in fact, we can do it exactly using the integral. We're not quite there yet, but that's the concept. Okay, so we already know that if we take this thing and we take the limit as n approaches infinity, we wind up with this approaching this limit, and we actually wind up getting the real exact answer. So now, here's the part I'm not supposed to show you yet. I'm supposed to wait until a later lesson, but I've decided to go ahead and show you. If you take this limit as n approaches infinity, delta x, the width of the rectangles approach nothing. So as n approaches infinity, what's the addition of all of those? Da-da-da-da-da! The integral. And the integral will give you the answer exactly. Now, what's a little different from this integral, from the one I showed you the other day? Notice it has two numbers here. So when you have an integral like this, that's called an indefinite integral. It's just a general integral, but when you have these two specific numbers from what to what, that's called a definite integral. Well, you can see it right down here too. Definite integral. And I'll be showing you how to do that. But anyway, I wasn't supposed to do this, but I'm showing you, hey, this is where this is headed. When you take these limits, oh my goodness, the integral actually does it for you. It finds the exact area under any exotic shape. It doesn't matter what it is, as long as it's, you know, it's differentiable, and therefore you can find the integral. So that's kind of where we're headed, but I'm going to make your assignment really simple. By the way, if you look in the book, the assignment says for 5.2, core exercises, they say 1 to 11 and then 15, 17, 37. So what I'm going to have you do is just do 1 to 11 odd, because we haven't had the time to go into the depth. Okay? So on 1 to 11 odd, at least this is the beginning part of that, you see problems that look like, well, these are the first 5 anyway. So let's work on these a little bit. And then I got a really cool thing I want to show you in Desmos. So you notice how it says find the sum, and then it says use the summation capabilities of a graphing utility to verify answer. That I'm going to show you in Desmos. Okay, so let's take number 1. You're supposed to add up 3i plus 2 when I equals 1 and counting up to 6. So when it's 1, 3 times 1 is 3 plus 2 is 5. Okay, my pen bugged out again. Come back. Trying to get my pen back. In the meantime, I'll try to write with my cursor, which is always fun. 3 times 1 is 3 plus 2 is 5. Come on. So the first answer is 5. And then when I is 2, 3 times 2 is 6 plus 2 is 8. Let's see if my pen is back. Yep. And then when I is 3, 9 plus 2 is 11. And when I is 4, 12 plus it's 14. So you can see how it goes up by 3 each time. And then when I is 5, 15 plus 2 is 17. And finally, when I is 6, 3 times 6 is 18 plus 2 is 20. And then you can add them up. And the answer is 75. Okay, so they're just trying to see if you get the notation here. Now, cool, watch this. So I'm going to show you in Desmos. How to do that. So they wanted you to check that thing, right? So here's how you do it. By the way, you can use the menu. You see down here at the bottom where it says functions. You can click on functions and then go to miscellaneous. And you'll see there's a sigma. And when you type that, you see how it pops up there. But even better, you can just type SUM, the beginning of the word summation, and it'll automatically pop up an integral. Okay, now you see how it's set there, n equals, and it's not I, but it's the same thing, 1, and then put 6 on the top, from 1 to 6, and then parentheses, and now I can't use I because my index is now n, so 3n plus 2. And do you see how it has the answer there? 75. So that's what they mean by you can check this, and Desmos works beautifully for this. Let's go back now to, let's do another one. Let's do number 3. So what do we got going on here? Well, when k is 0, we've got 1 over 1, which is 1. When k is 1, 1 over 1 squared plus 1, so 1 over 2. When k is 2, we've got 1/5. When k is 3, we've got 1/10. And when k is 4, we've got 1/17. So there's the, there's the, what it's actually asking you to do. And I don't want to take the time right now, but you can actually, this is what? 1 plus 0.5 plus 0.2 plus 0.1. And 1/17 is, you can actually do that. Anyway, the whole thing turns out to be 1.8588. Let's check it in Desmos. So now, SUM for summation, symbol pops up. Yeah, we were on K, and Desmos wants you to use N. So anyway, just do 0 through 4, I believe is what it said. Is that right? I think so. No, it was 1 through 4. Huh? That's a problem. I can't see everything at the same time here, but I think it's 1 to 4. And it's 1 over n squared plus 1. Oops.
I think it was 0 to 4, actually.
Was it? Okay, thank you. I don't know what's going on here. Let's try this again. So it was 0, 4. Whoop. And 1 over, was it k squared? What did it say? K squared plus 1. So in this case, we're going to say n squared plus 1. Sorry. And then we got to put what am I missing? Need parentheses. I'm sure what I'm wrong there. But anyway, so up here we had no problem. N equals 1 to 6. N equals 0 to 4. It should work.
Maybe
I
the
don't know.
parentheses. Because you had parentheses.
Yeah, possibly. Let's try that. Oh, there we go. I had that exponent in there. Anyway, you can check your work that way. It's pretty cool. Desmos will allow you to do that. All right. So back we go. What's number 5? Well, that's one of those no-brainers. Add up the same number C 4 times. Right? It says add up C. I mean, you notice there's no K in the problem. So just add up C, add up C, add up C, add up C. So pretty obvious the answer is just going to be 4C, isn't it? Okay. Anyway, what's the next? Okay, the next branch. This is interesting. They're trying to get you just a little bit into sigma notation. So we're supposed to write sigma notation for these, for what we've got here. I don't know why my pen goes away. Trying to get it to come back again. So come on. Okay, pretty hard to do without the pen, so I'm going to give it a shot with the mouse. So here we go. How could I write this top one in sigma notation? Equals. Okay, so we're going to have a sigma, and we're going to have an I. And you can notice, do you see how this is, what's the same up here? Do you see how 1/5 is in every problem? Every one of these things to be added up. And then the 5 is multiplied by with the index, which starts at 1 and goes up to 11. So you see where I got those from, right there and right there. And then that's supposed to be an I. Let me try using the pen now. Yeah, now it's back. So let me try that again. So that's 1 over 5I. Does that make sense? So what you want to do is the part that repeats, that goes in your sum, 1 over 5. And then the denominator is multiplied by this thing that counts each time. And you can see it starts at 1 and it goes up to 11. Okay, so let's try number 9. And change to blue here. So sigma and if there's a counter, do you see how it's this right here? It's this numerator in this thing over 6. You see that? And it looks like it goes from 1 to 6. Now what's the same? Well, every one of them has a 7. multiplied by whatever I is divided by 6. And then there's a plus 5. So the 7, the denominator of 6, and the addition of 5 is the same in every fraction. The only thing that changes is that one numerator. So this would be a way to express that. All right. Let's try one more. How about if we look at number 12? So we've got our sigma notation. We want to locate the things that seem to stay the same. So here we have, here's our first term. Yeah, pen is out again. Here's our first term. Okay. And then what's different over here? And the answer is nothing. So basically, we've got that whole thing that repeats is 2 parentheses 1 plus 3. Trying to do this without a pen. Come on. Squared. And then that whole thing multiplied by 3 over n. And that just looks like it just gets repeated what? We don't know how many times. Looks like it goes for an infinite number of times from what the notation shows. So I equals 1. And I don't see any end to it. I mean, it doesn't show any, we don't know how many, or I suppose n would be fine here. So let me change that to an n. So you get used to it, but you want to basically put the part in there repeats and then watch for the thing that changes. On number 10, you see how what changes is, here we have a 1, 2, and it ends up with a 4. So that would be your I equals 1 to 4, and then that would be where you'd put your I. So anyway, just trying to get you used to this sigma notation. So that's it today. Hopefully you've learned a couple things that how do we actually know now how we wind up with an integral being an area. It actually is a sum of the area of a bunch of little skinny rectangles. And if you take the limit and have an infinite number of rectangles, it becomes eventually, not today in this lesson, but eventually it becomes a good old integral. And even though I taught you, we went through indefinite integrals where there's no limit. Let me just refer back to what I'm talking about here. Indefinite integrals where there was no top or bottom. You know, there was no right here or right here. Just a generic integral, kind of like a generic derivative. And later, we're going to learn that we can actually have numbers in the A and the B position. Then it becomes a definite integral, kind of like the difference between f prime of x and f prime at 2, where you find a specific, the same kind of thing. We haven't gotten there yet, and we will be, I think we'll be talking about that probably tomorrow or Friday. So for this time, let me just remind you, I'm modifying the assignment. I just want you to get into the first 11, the odd. That's not very many to do, but you're just trying to get your head around this concept of adding up rectangles and getting used to this sigma notation. This, by the way, called a summation. And that's why in Desmos, the shortcut is SUM. It's the beginning of the word summation. Okay. Questions? Sorry about my coughing and sniffling. Have a good one. Thank you.